Alright, and this exercise, I'm going to show you one more time how to evaluate the work required to assemble charges together from infinity, or the energy stored in a given configuration. In this small question, we have small deviation, so let's follow. What is the work needed to bring this charge minus 5 nano from the position 30 centimeter to infinity? So I'm going to push this particle to infinity. How much work is required? So clearly I'm not really looking for the configuration energy or how much work to put them together. So they are here. There is some energy stored, but I am not looking for that. What I'm looking for is the work required to push this charge, which is negative, to infinity. So the final energy, absolutely, obviously, 0. So this is infinity is 0. Okay. So what is the area? I'm going to evaluate to find the energy here. This is the energy initial. So U initial. I have to find that energy, which is, of course, the change will be the work. So what is the initial? The initial is when this particle is interacting with the rest of the particles. So what is the strategy here? I'm going to evaluate the voltage due to these charges individually. That net voltage times the charge minus 5 is the energy of that particle at that position. Then the change to bring it to infinity, then the change infinity minus this energy. That's the work required to pull this charge from the set of charge. Okay, so that's the area. So let's evaluate the voltage here due to every charge. So the V, the voltage due to all charge is equal. So constant K that I'm going to factor out, then charge Q1 over R1 plus a charge Q2 over R2 plus charge Q3 over R3. What is R12? Well, R1 is here. This is R1. R2 is this one. And R3 is this. This is R3. Alright? So that I calculate using Pythagorean theorem. This is 30, this is 6 square root of, you have 30.6 centimeters. So that's it. So that is now explicitly, so this is 9, 10, so the 9 power. And then I have nano everywhere, nano, nano, nano. So I'm going to put nano outside, which is 10 minus 9. And then I have centimeters, so I am going to factor out also centimeter, which is 10 minus 2 meters. Now open. The charge Q1 is this, minus 3, and the distance is from 2 to 30 is 28, and centimeter is here, and then plus the contribution of this one, 2 nano. I have factored out 2 nano already, and the distance is from 12 to 30, and that is 18 centimeter, of course. And then the contribution of this charge 4, and the distance we have calculated 30.6. 30.6. Close. And if you do the math, you are going to find 121.2 volt. All right. Now, if you know the voltage at this point here, and you know the charge, you can evaluate the energy at that point. So the energy U at that point, which is initial, is just the charge, which is minus 5 nano like so, times the voltage at that point, which is 121.2. All done. You are going to find so you are going to find 0.061 joules, minus, of course, minus 0.61 joules. So this is the energy stored at this point in this particle. The question is, how much work is required to bring this charge from this position to infinity? So the final energy is 0, the initial is this one. So the change in potential energy is U final, which is 0, minus U initial, which is 0.61, which is equal to 0 minus 0.61, which is equal to plus 0.61 joules. All right. It is not joules, actually microjoules. This is micro. I have micro here. Let's put, this is micro. All right, let's remove this one here. So this is micro joule. That means 10⁻⁶. This is also microjoule. Alright, so this is the energy. I have to add this particle to free it to infinity. Alright,